Hi everyone, I'm Shaghayegh Roohi from Aalto University, Finland. Today I'm presenting recognizing emotional expression in game streams. You know that we cannot separate emotions from games. Some study equates emotions with positive player experience. Some others know emotion as key factors in defining fun. And also, we know that there is this public and underexplored resource of game stream videos. You can see here an example of the game stream that we've used.
What is that?
You can see the player how show his emotion and even narrates his feelings. So we decided to investigate emotions inside game streams to see if we can detect the human annotated emotional events in those streams, and if we can identify the most intense events of game streams. We have two contributions in this paper. We have presented a new data set of emotional events in game stream, which contains 17 videos, around 2,000 emotional events. We also present a multimodal neural network for detecting these emotional events automatically, which uses facial expression recognition, speech sentiment analysis, audio emotion analysis, and also audio features like loudness and pitch. For dataset, we use Unravel and Unravel 2 games, which are puzzle platformer games. We selected these games because they are recently released and there are multiple streams available for them. And also they have linear level design, so we expect that players experience game events in the same sequence. And both of them have been praised for being emotionally engaging. Our criteria for selection game stream is that the face of a streamer should be visible throughout the video, a streamer should speak in English, and only one person was playing and present during a stream. Also, the automatic captioning is available for the game stream. This process resulted into 17 videos by 9 different streamers, 2 women and 7 men. Each video has been annotated by 2 annotators into 13 classes of emotions like happiness, amusement, startle. And also each emotional event have been labeled as being top 5 event or not top 5 event. We tried 4 types of classification. The first one uses no event and event class. The second one uses top 5 event and not top 5 events. The third one uses 4 classes of no event, pleasant, unpleasant, and neutral event. Pleasant event like happiness, amusement, and unpleasant event like startle, frustration. Neutral event like moved and wonder. The last one uses no event class and all 13 classes of emotions available in the dataset. As I told, each video has been annotated by 2 annotators, so we calculate their human agreement for each video, and as you can see, the human agreement decreases with more fine-grained classes. So, for example, you can see 14 classes is not very reliable, and with larger window lengths, because we use a time window that go along the whole video for predicting this human agreement. And with larger window lengths, the human agreement increases, but we kind of lose temporal resolution. In our automatic detection system, we apply facial expression analysis on streamer face, we apply audio analysis on streamer voice, and also sentiment analysis on streamer's speech. All of these modules are trained on public large data set, which outputs the probability of different basic emotions or positivity of a speech. Output of these modules are time series signals. We combine these time series signals in a time window using a temporal neural network, which is trained on our smaller and custom data set. And this neural network outputs the probability of emotional event. Here you can see an example of our input signal. As I told, in a large time window, we kind of lose temporal resolution. So you can see that one annotator detected 2 events in this time window. And another thing is that you can see one annotator detected this event as a startle and the other one detected it as surprise. Because surprise and startle have similar expressions, they are harder to be distinguished by humans. And here is an example of a game stream alongside the input signals. Here you can see the results of our automatic emotional event detection. We used different combination of input signals, and the first column shows just using facial expression, second one facial expression and sentiment analysis, third one facial expression, sentiment analysis, and audio emotion analysis. First one, facial expression, speech, sentiment analysis, and audio features like loudness and pitch. The last one uses all input signals. Here again, like human agreement, the performance decreases with more fine-grained classes, and you can see that window length of 1 almost always produces the worst result, but we cannot see a significant difference between other window lengths. At least in our case, facial expression and audio features were the most informative signals. And the facial expression, sentiment analysis, and audio features produces the best results here. But adding more input signals cannot help us every time. The reason may be because of overfitting, since our data set is fairly small. Unless the input signal is very informative, adding more input signal can lead to overfitting. And another thing that I want to mention is that our audio emotion analysis had good results on audio data sets. You can find more details on the paper about that. But the performance of it during applying on game streams reduces. And the reason is that because here, besides a streamer's voice, we have game audio as well. Here you can see percentage of missing events using the best performance of 2-class model. Our classification, as our system is mostly has good performance on detecting positive emotional expression, and some subtle emotions like moved, wonder, and puzzlement have high false negatives, maybe because that they have lower intensity expression. And also high amount of false negative for negative emotions like frustration and startle, maybe because that they are immediately followed by positive, immediate positive expressions like smiling. As future work, we want to add annotation of gameplay events as a complementary material. We want to investigate the effect of differences in gender, age, and culture on our system. And also we want to test our system on playtest videos without game audio. In summary, we presented a new data set of emotional events in game streams. We have presented an automated detection of emotional events in game stream using multimodal neural networks. And we show that identifying emotion is a hard task for both human and artificial neural networks, but with limited number of classes, we can get reliable results. We get, for example, in case of just detecting events, we get automatic detection accuracy of 70%, which is on par with human agreement of 68%. And this suggests applications in video highlight detection and pre-screening videos for later analysis. Thank you.
debate is open for questions. Here's one.
Thank you. Very nice paper. Nice analysis of the results.
Thank you.
And I like this progression from 2 class to 14 class results. I see the challenges.
Yeah.
But I have a question basically about what's on here. Automatic detection accuracy of 70% comparing to the human-annotated agreement. And in the big table, we also saw 80% accuracy for like the 2 class to window, no, the 3 class to window.
Yes.
Anyways, how do we interpret 70% accuracy in case of 86% human-annotated reliability? Because that's not entirely evident to me what it means to have an accuracy of 70% now.
Actually, that's a good question. Thanks. The human agreements cannot completely. It's not completely comparable with automatic detection analysis. Since in case of human agreements, one person tries to predict another person, but here we kind of try to predict the average of annotations of players. Because of that, they are not completely comparable.
Yeah, but the 70% seems to assume some kind of reference to a ground truth.
Okay.
But a 68% human-annotated agreement kind of suggests that we don't really have a ground truth. So shouldn't you need to do an extra layer of analysis taking the automatic detection back to humans and say how meaningful and recognizable is the outcome of my automatic classification afterwards for human assessors?
Yeah, actually that would be interesting to investigate. Yes, I guess.
Okay, so like suggestion for future work, maybe. No, I don't know. I mean, it's not meant as a critique, but as a suggestion.
Yeah, thank you.
Further questions? Yes, I'll say your name again and your affiliation.
Yes. Hi, Ansgar Depping, Electronic Arts. Thank you so much for the talk. I'm really looking forward to reading this paper. Could you, I'm sure it's in the paper, but could you describe a little bit the setup and how you prompted your participants so that they emoted so strongly as they did in the videos?
You mean?
Oh, these were game streams
from,
and then where did you get them? I'm sorry, I hope you didn't say this.
YouTube.
Oh, okay.
All of them, yeah.
Well, in that case, don't you think there's a little bit of a performative aspect?
Yeah, sure. There is, I guess, we have this problem with game streams. They kind of exaggerate their feelings, but we can apply this method on video playtests that are more realistic. But even in case of game streams, it is good that they kind of narrate their feelings because they want to attract their viewers and. Because of that, for example, we less see the gaming phase and this stuff. Because of that, yeah, I guess it's worth analyzing. Yeah.
Thanks.
Thank you.
Time for one more question. Let's see. Continue.
Hi, Listener Rock from the University of Coimbra. Maybe I missed this, but did you train the classifier for each specific video feed source, or
No.
is it just the same classifier for all?
For all.
Thanks.
Okay, so let's thank Shaghayegh again for the and we stay emotional with the next presentation, and to spice it up a bit, I have the second one of these honorable mentions for Julia for this paper. So you didn't expect that.
No. Thank you very much.